Today we will discuss about Fourier transform. This is the third transform. First is Laplace transform, second Mellin transform, third is Fourier transform, and the last one is Hankel transform. Today we will discuss about Fourier transform. Fourier sine transform, Fourier cosine transform, and complex Fourier transform. First, we will discuss about Fourier sine transform. The infinite Fourier sine transform of fx when x is between 0 and infinity, denoted by fx with parameter p or fs bar p, and defined as fsp bar 2 upon under root by 0 to infinity sin px fx dx, whenever it exists and p belongs to n. P is a natural number. Second one is Fourier cosine transform. The infinite Fourier cosine transform of fx when x is between 0 and infinity is denoted by fcp bar or fcp fx with parameter p, and defined as fcp bar is equal to 2 upon pi under root 0 to infinity cos px fx dx, whenever it exists and p belongs to n. Some authors define these transforms as follows. Fourier sine transform is defined as fsp bar is equal to 0 to infinity sin px fx dx, and Fourier cosine transform is defined as fcp bar integral 0 to infinity cos px fx dx, where p is a natural number. Next, Fourier transform or Fourier complex transform. The Fourier complex transform of fx when x is between infinity, minus infinity to plus infinity, denoted by fp bar, and is defined as f bar p is equal to 1 upon under root 2 pi minus infinity to infinity e raised to power iota px fx dx is equal to fxp, or some author defined it as minus infinity to infinity e raised to power iota px fx dx. Properties of Fourier transform. First property is linearity property. Linearity property of Fourier transform. These properties are same for Fourier sine transform, Fourier cosine transform, or Fourier complex transform. We will discuss these properties for Fourier complex transform. If f bar p and g bar p are Fourier transforms or fx and gx respectively, then Fourier transform of a fx plus b gx is equal to a f bar p plus b g bar p. Fourier transform of fx with parameter p is equal to 1 upon under root 2 pi minus infinity to infinity e raised to power iota px fx dx is equal to f bar p, equation first. Similarly, we can write the definition of Fourier transform of gx with parameter p will be equal to 1 upon under root 2 pi minus integration minus infinity to infinity e raised to power iota px gx dx is equal to g bar p, equation second. Now Fourier transform of a fx plus b gx will be equal to 1 upon under root 2 pi minus infinity to infinity e raised to power iota px a fx plus b gx plus dx is equal to a upon under root 2 pi minus infinity to infinity e raised to power iota px fx dx plus b upon under root 2 pi minus infinity to infinity e raised to power iota px gx dx. A f bar p plus b g bar p. This is called linearity property for Fourier transform. Second one is change of scale property. If f bar p is the Fourier transform of fx, then the Fourier transform of fx is 1 upon a f bar p upon a, or f Fourier transform of fax with parameter p is equal to 1 upon a f bar p upon a. We can define Fourier transform of fx with parameter p as 1 upon under root 2 pi minus infinity to infinity e raised to power iota px fx dx. Now, Fourier transform of fax with parameter p will be equal to 1 upon under root 2 pi minus infinity to infinity e raised to power ax fax dx. On putting ax is equal to t, so that dx is equal to dt upon a is equal to 1 upon a 1 upon under root 2 pi minus infinity to infinity iota p upon a t ft dt 1 upon a f bar p upon a. This is called change of scale property for Fourier transform. Next one is shifting property. If f bar p is the Fourier transform of fx, then the Fourier transform of fx minus a is e raised to power iota pa f bar p. Fourier transform of fx is defined as 1 upon under root 2 pi minus infinity to infinity e raised to power iota px fx dx is equal to f bar p. Therefore, Fourier transform of fx minus a with parameter p will be equal to 1 upon under root 2 pi minus infinity to infinity e raised to power iota px fx minus a dx. On putting x minus a is equal to u or dx is equal to du, this integral becomes 1 upon under root 2 pi minus infinity to infinity e raised to power iota p a plus u fu du. E raised to power iota pu e raised to power iota pa 1 upon under root 2 pi minus infinity to infinity e raised to power iota pu fu du, or we can write this one as e raised to power iota pa f bar p. This is called shifting property for Fourier transform. Next property is modulation property or modulation theorem. If f bar p is the Fourier transform of fx, then the Fourier transform of fx cos ax is 1 upon 2 f bar p minus a plus f bar p plus a. This is called modulation theorem. If we take Fourier sine transform instead of Fourier transform, then this will become fs bar p minus a fs bar p plus a. When we take Fourier cosine transform instead of Fourier transform, then it will become 1 by 2 fc bar p minus a plus fc bar p plus a. Fourier transform of fx with parameter p is defined as 1 upon under root 2 pi minus infinity to infinity e raised to power iota px fx dx. Now, Fourier transform of fx cos ax p will be equal to 1 upon under root 2 pi minus infinity to infinity e raised to power iota px cos ax fx dx, or this cos ax may be written as 1 by 2 e raised to power iota ax plus e raised to power minus iota ax by 2. 1 by 2, 1 upon under root 2 e minus infinity to infinity e raised to power iota p plus a into x fx dx plus 1 by under 2 minus infinity to infinity e raised to power minus iota p minus a fx dx. This is Fourier transform for fx of fx with parameter p plus a, and this is Fourier transform of fx with parameter p minus a. This is called modulation property or modulation theorem for Fourier transform or for complex Fourier transform. Relationship between Fourier and Laplace transform. Laplace transform of fx is defined as 0 to infinity e raised to power minus px fx dx. If we define fx as e raised to power minus alpha x gx when x is greater than 0 and 0 when x is less than 0 by the definition of Fourier complex transform. Fourier complex transform is defined as f bar p will be equal to minus infinity to infinity e raised to power iota px fx dx. Fourier transform of fx with parameter p is defined as integration minus infinity to infinity e raised to power iota px fx dx. Breaking this limit into minus infinity to 0 and 0 to infinity. Minus infinity to 0 e raised to power iota px fx dx plus 0 to infinity e raised to power iota px fx dx. Between these limits, when x is less than 0, the fx is 0, therefore minus integration minus infinity to infinity e raised to power iota px into 0 into dx plus 0 to infinity e raised to power iota px e raised to power minus alpha x gx dx. 0 plus 0 to infinity e raised to power iota p minus alpha x gx dx, or integral 0 to infinity e raised to power minus alpha minus iota p x gx dx is equal to 0 to infinity e raised to power minus sx gx dx, where alpha minus iota p is equal to s. This is the definition of Laplace transform of gx. Therefore, Fourier transform of fx or f bar p or Fourier transform of fx with parameter p will be equal to Laplace transform of gx when gx is defined as given function. Let us discuss an example. Find the Fourier sine transform of fx when fx is defined as sin x when x is between 0 to a and 0 when x is greater than a. Fourier sine transform is defined as fsp bar is equal to 2 upon pi under root integral 0 to infinity fx sin px dx. Breaking this limit into two intervals 0 to a and a to infinity. When x is greater than 0, greater than a, fx is 0. When x is less than a, then fx is equal to sin x. Fs bar p is equal to 2 upon pi under root 0 to infinity fx sin px dx. 2 upon pi under root 0 to a fx sin px dx plus a to infinity fx sin px dx. Putting the value of fx, when x is greater than a, this will become 0, and when x is less than a, fx is equal to sin x. Here sin x, sin px multiplying by 2 and divided by 2. This will become cos 1 minus p into x minus cos 1 plus p into x and dx. Integrating sin 1 minus p x upon 1 minus p minus sin 1 plus p upon 1 plus p into a, putting the limit from 0 to a. When we put 0, sin 0 is equal to 0 and we put x is equal to a, then this will become sin 1 minus p a 1 minus p upon 1 minus p minus sin 1 plus p into a upon 1 plus p.